Alrighty, this is the last video for 9-station review, station 7, 8, and 9. And right out of the gate here, they ask a very difficult question. Well, first of all, you have to match the statement with the interparticle forces. That's all you're thinking about now is interparticle forces. Is used to explain why the boiling point of xenon, krypton, argon, neon, and helium, well, why xenon's greater than krypton and krypton's greater than argon, why the boiling points of each increase. First of all, you have to look at the type of atoms that they are. They're noble gases. Noble gases do not react. They are not polar because their electron shells are filled, right? So these things are non-polar atoms. They're very non-reactive, non-polar, hence they're noble gases. For non-polar atoms and molecules, the only interparticle forces at play is London dispersion. London dispersion. Tricky question. You probably will not see it on the test. Is present in graphite and diamond. Well, graphite and diamond, let's remember what they are. They're network covalents, right? Network covalent looks like this. It's a network of covalently bonded nonmetals. It's a network of covalently bonded nonmetals, all bonded to themselves. That is network covalent, you guys. Okay, network covalent. Where is it? I can't find it now. Oh, well, it's not there. So it's covalent bonds. Covalent bonds is what's holding the network covalent structure together. So it's covalent bonds. Is used to explain why copper is a good conductor. Copper is a metal, and the sea of electrons model tells us that, hey, there's delocalized electrons around the central atom, and those things carry charge. You can pass a charge easily through metals as a result. Is used to explain why NaCl is a good conductor. Well, NaCl is held together by ionic bonds, and whenever you dissolve it in water, the positive ions and the negative ions also carry a charge. So that's D, ionic bonds. Is used to explain why ICl has a higher boiling point than Br2. ICl, Br2. ICl is non-polar. Br2 also non-polar. Actually, wait a second. Is that right? That's not right. ICl looks like this. And we said the four strong are nitrogen, oxygen, fluorine, chlorine. Well, this guy is polar. Okay, ICl, that guy is polar. Br2, bromine bonded to itself, non-polar. So that one's polar, non-polar. Okay, so if it's non-polar, then what forces are at play? London dispersion. If it is polar and there's no hydrogen, then that's dipole-dipole, which is stronger than London dispersion. So that would make sense. So dipole-dipole interactions, A. Is used to explain why the boiling point of CH3OH is higher than CH4. Well, the same principles apply here. Here's CH4. CH4, non-polar. Okay, CH3OH, do you guys remember what it looks like? CH3OH. This thing is polar. Anytime you got a polar molecule, oh, and look at that, it's got an oxygen in it. Okay, so if it's got that negative, partial negative oxygen, that means it's going to react with any, not react, it could do a hydrogen bond with any other hydrogens nearby. So if I had another one of these nearby, I'll just draw two of them so we can see. CH3 OH, there's your partial negative. Okay, let me draw another one over here. Okay, so let's say there's trillions of these things in a beaker together. Okay, well, what's going to happen these partial negatives on the oxygen are going to be attracted to the partial positives of the hydrogen. So that is a hydrogen bond. That's a hydrogen bond right there. Okay? So let's go ahead and answer that then. Is used to explain why the boiling point of CH3OH is higher than that of CH4. CH4 doesn't have, it's nonpolar. The only forces acting on CH4 is London dispersion. Whereas in CH3OH, there's hydrogen bonds. It takes a lot more energy to break hydrogen bonds. That's why it's got a higher boiling point. Okay, that's why water's got such a high boiling point. A lattice of positive ions in a sea of delocalized electrons is metallic. Positive ends of molecules attract the negative ends of other molecules. That is dipole-dipole, you guys. That's the definition. Lattice of alternating positively and negatively charged particles. Okay, the key is this now. Here is the key to understanding that question. You got positive, negative. That's a salt. Positive, negative, ionically attached to one another in a lattice. A salt, all salts are ionic. Those are ionic bonds. Hydrogen atoms tethered between small, highly electronegative atoms of N, O, and F. That is the definition of a hydrogen bond. Oops, let's see, hydrogen bonding. Polarized electron clouds induce dipoles in their neighboring atoms. That's dipole-dipole. Hey, I would save this. This has got all the definitions on it. Drill yourself on this one. Drill yourself. See if you understand it. If you don't understand what this means, you need to see me so I can explain it in detail further. Although it was in the notes, explained in detail as well. Okay, let's go on to the next one. Oh, I don't know if I'm going to have enough time to do all these. Indicate the strongest interparticle attractions in each of the following solids. Here's what you have to do first. Identify if it is a metal. Identify if it's ionic. Because if it's ionic, we know that it's going to be ionic bonds. K2S. Ionic bonds. Sodium, just straight up metallic. Okay, we've done that. Then go through and see if you can find which one of the remaining covalently bonded molecules are nonpolar. If they're nonpolar, it's going to be London dispersion. CH4, nonpolar. London dispersion. H2S, nonpolar. London dispersion. Let's see, any other nonpolar ones? Nope. Okay. Now we look at the ones, oh, look at xenon. Yeah, London dispersion. The rest of them are polar. Why are they polar? You've got a strong bonded to a weak. Strong bonded to a weak. Strong bonded to weak. Strong weak. Strong weak. Strong and weak. The rest of them are polar. Now you got to go through and go, are there any that are just dipole-dipole that do not have oxygen, nitrogen, or fluorine in them? And that's going to be this one right here. That's polar. It does not have oxygen, nitrogen, fluorine, so it's going to be dipole-dipole. This one does not have hydrogen in it, although it's got oxygen. So it's incapable of forming a hydrogen bond. That's also going to be dipole-dipole. Oh, look at that. CO2, nonpolar, right? CO2 is nonpolar. I missed that one. That's London dispersion. Silicon dioxide does not have hydrogen in it, so that's going to be dipole-dipole. It's polar, but it doesn't have hydrogen. Oh, actually, it may not be polar, is it? Silicon dioxide is the same as carbon dioxide. Here, don't believe me? Let's draw it. Yep, see that? If I were to clean it up, it would look like this. Oh wait, that's disilicon. What am I doing? Moderis. Sorry, ignore that. Look like this. There we go. Okay, and if I were to clean it up, it would look like this. These polar bonds cancel. Okay, so silicon dioxide, not dipole-dipole, that's London dispersion. Okay, that leaves us with NH3. NH3 is capable of forming hydrogen bonds. Okay, because hydrogen bonds occur with N, O, and F. And CH3OH, we already looked at that one many times, at least twice. That's hydrogen bonds. Okay, I know that's difficult. That analysis is tricky, I know. Let's list 3 examples of network covalent solids. Diamond, graphite, and quartz. Okay, I've already gone over where I should be in this video, so I'm going to go ahead and make one last video then.